I'm your mental curator, Johnny Hemberger, YouTube and podcast manager here at the Houston Museum of Natural Science. Not only is science obviously everywhere at HMNS, but scientists are too. Meet Alex Ruff. Alex is the building manager here at HMNS. He knows every nook and cranny of the building, and when any of our objects come to life overnight, he's the first line of defense in making sure our dinosaur skeletons don't escape. Alex is also a passionate, well-versed geologist with a rock-solid degree in geology. Not only is he an expert in this field, but he is also just a truly wonderful, hardworking, awesome guy. For this episode of the HMNS Beyond Bones podcast, I had the privilege of meeting Alex in front of the world-famous Alma Queen Rhodochrosite specimen to talk about the Alma Queen and so much more mining of the mind. All right, welcome to the HMNS Beyond Bones podcast. My guest this week for this episode is Alex Ruff. Alex is the building manager here at the Houston Museum of Natural Science. But there's science everywhere in this museum. Alex is actually a geologist. So can we just talk about your story in the field of geology, kind of where it started and how that happened for you?
Yeah, so originally when I went to college, I went to start business because I wanted to, own a restaurant and things like that. But growing up, geology was always a passion, collecting rocks, like most kids do. But I took a geologist class in my undergrad, and that sparked a real passion. So I actually switched degrees and finished off with a degree in geology and started in the oil and gas field, but it just wasn't the same.
Right.
Because that's what everybody does when they come to Texas, is they do the oil field. And so, but I found it to be more interesting to teach about geology and to learn more about the ins and outs of all different things. And mineralogy has always been a passion of mine. And so working for the museum was a way that I could definitely get into more gems and minerals and things like that. And so and I've held many positions here at the museum, but I've always had a real passion for geology.
Would you say that what's your aspiration within the museum? Would you love to be a curator of geology, or how far do you want to take it?
Yeah, absolutely. To be able to work with minerals and help the museum collection and learn more about people and all where they come from, and teach people about all these fascinating things and where they stem from in nature.
Right, and inspire that curiosity, because you never know who you're going to talk to, who you're going to teach about, for instance, the Alma Queen here, or any of these fantastic specimens we have. And in my opinion, they are presented in a truly breathtaking manner.
Yeah, absolutely. So the one thing that Joel and the museum have definitely done with these minerals is really highlighted the natural beauty. There's no snuff about it. It's just the mineral in its purest form.
Right.
Beautifully lit in the best fashion right here in this hall. With the black backgrounds and the beautiful lighting, you see the beauty for what it truly is.
Right, and that's one thing that I love about it too. You can see on camera here, and I will show some B-roll while we're talking here also. It is, I would call it minimalist.
Yes.
It's a black background, just a jet black background, so you can really see the mineral for what it is in all of its natural glory. There's nothing kind of around it to distract from it. You can see right here, the Alma Queen is just, it's literally on its pedestal. It's literally in the spotlight. Can you speak a little bit to, if you can, the unique lighting in this hall?
These cases specifically are unique in such a way that each little light, it can be moved and positioned.
Right.
The color of the light and the temperature can definitely highlight and blend well with the mineral, and you can pinpoint the structure, the colors. You can actually move them so that they're backlit, and it's just amazing what these cases are able to do. They're not just your simple put a light on the mineral. They're built so that they're encased, but they're also humidity controlled, temperature controlled. So it's very specific, and it's designed to really make sure that these things are shown in the best light. No pun intended.
Right, and that they're protected in the best way. Y'all can see that we are in a functioning working museum here. So I like doing these podcasts kind of among the people. So if people come swinging through the frame here, we're a museum that's hopping today.
And anytime anybody's talking about these, people have to know what's going on, and they want to know, they want to learn. That's why they're here. This is what we're great at doing, is teaching.
Right. So when we find these minerals, we are protecting them. It's not exactly hermetically sealed, I don't think. It's probably not. Maybe it is, maybe it isn't. It's not like a vacuum inside of there, but it is protected from obviously erosion, from wide temperature fluctuations that could cause fissures and cracks and things in the gem. My eyes are bad. You can tell by the thickness of my glasses that my eyes aren't great. But in here, it's like looking at things in 8K. Like it's super crisp, super sharp. Even the glass here is immaculate. The glass here that they use seems like a mineral in itself that should be on display because of the clarity and all that, which I'm sure is on purpose. Speaking of clarity, speaking of all the little different data specs, qualifiers for minerals, can you walk us through
what makes a mineral a mineral?
What makes a mineral a mineral, and what all those little numbers mean when you're looking at?
Absolutely.
Sure.
So to determine a mineral is quite a process. It's not just people who have been in the field for long enough can look at a particular mineral, know exactly what type it is. And Joel, our president, he can actually look at a particular mineral and know exactly which mine it came from.
Right.
But that's with experience in the field and things like that. So we'll show some other minerals here in a minute, but some are unique to specific regions in the world. And so, for example, the Alma Queen is unique specifically to the Sweet Home mine in Alma, Colorado.
Right.
Now, what makes this specific specimen so unique is the rarity because of the color.
Right.
So if you look up Rhodochrosite on Google, you'll see a bunch of different varieties. Now, some kind of have this bubblegum pink, some can be a little brown or white, and those are actually impurities in the mineral structure that gives it that different color.
Right.
So with Alma, their unique experience with Alma specifically, it's the lack of impurities that gives it that bright red color.
Yeah.
So iron is a naturally forming metal, and whenever minerals are formed, they collect the different material around them as they're forming, and in the form of atoms to build its structure.
Right.
And so when you have iron present or high levels of iron, that will act as an impurity. And now we don't mean it so much as a bad thing, but it's not as clean and pretty as you would see in a gem quality. But this particular one has very low levels of iron, which makes it that red. And this is one of the only places in the world that can actually be this red. So that's why Alma, Colorado is the place to find rhodochrosite this red.
Am I off base? I did a podcast maybe a year ago or earlier in 2025. I forget exactly when. This is kind of a follow-up podcast to that because one of the questions was, well, some people say that this is the best specimen of any mineral ever. How do you? And that's all subjective, and we'll talk about that in a minute. But am I far off base? Is it the level of manganese? Is that there's a mineral? There's another mineral that you were just talking about. What determines the color of?
Yeah.
And it basically is. I don't know. I'll double check that. I'll put that in the notes or on the screen somewhere if it's manganese. Maybe I'm just thinking of manganese because I've been taking magnesium recently for my leg, which is a different thing. But
so funny enough, exactly. So using it as an example, so rubies and sapphires.
Yeah.
So they're both actually the same mineral, but due to levels of the elements in their structure, that's what alters their color.
Right.
So beryl is the overall classification of minerals that fall under like emerald, and it's all made of the same stuff. But for example, emerald has high levels of chromium-3 ions, which gives it that bright green, beautiful color.
Cool.
And so to determine if it's actually an emerald or just a very green aquamarine is to look at the levels of chromium-3 ions in the mineral itself. So with this one, yes, the higher concentrations of the pure chromium not chromium, but manganese, or magnesium. This one I think is manganese.
I believe that's right. I will put on the screen. I'll make double sure that we're talking about the right element here.
So yes, it's just manganese carbonate. So it is what it is.
I'm not second guessing the geology.
No, of course.
I will trust but verify.
So if you hadn't noticed, mineralogy is heavy in chemistry. So basically the chemical formulas of these minerals will determine what a mineral is. And so how scientists determine what minerals are is using what's called XRF, or X-ray fluorescence, which is actually measuring the quantities of certain elements in the mineral.
Cool.
And so they use different tools like XRF, XRD, and so spectroscopy and diffraction to determine exactly the quantities of each one. And then so you look at a chart and say, oh, this is manganese carbonate, and it has this many manganese atoms, this many carbonate atoms,
Right.
and therefore it has to be this. Now, there are some easier ways to determine minerals from like a student standpoint, stuff that we're taught in school. You would want to look at the hardness. So the hardness scale, most people
Right.
know about the Mohs hardness scale, diamond being 10, the hardest.
MOS, right?
MOHS,
MOHS, yeah.
I believe.
Yeah.
And so 1 being talc and 10 being diamond, that is the scale of hardness in the mineral world. So all minerals have a hardness. Now, I can't exactly remember what rhodochrosite is, but I think it's like 6 to a 7.
That sounds about right. I'll put the stats on the screen.
Yeah, and so you would test the hardness basically by scratching it with maybe a nail. Like your fingernail can also scratch some minerals. You can use a steel knife or a ceramic tile,
Right.
and even glass, because quartz is a 7 to an 8 on a Mohs hardness scale. It can scratch a piece of glass.
Right.
And so it's one of those things that you would use to determine what it is if you don't have a very expensive spectroscopy machine.
Right.
But I realized I skimmed over the part, like what makes a mineral a mineral. So there are defining classifications that says that this is a mineral. So it has to be naturally forming, meaning that we can't make it in a lab.
Right.
It has to be inorganic, which means that it can't be made by a living organism. So like pearl, mother of pearl, things like that is actually created by a living organism. So
Like mollusks and things.
yeah, so it can't technically be a mineral. It is a precious gem. So the qualification of being a gem versus a mineral, because
Right.
not all minerals are gems, but some gems are minerals.
It's this Venn diagram of,
Yeah, exactly. And so you would assume that, like, some things kind of blend, like ice. Naturally forming ice, like in Antarctica, can be considered a mineral because it's naturally forming inorganic solid. Has to be a solid, no gas, or liquid.
It's blowing my mind that ice can be
A mineral.
a mineral.
Yeah.
Cool.
And then also it has to have a set, definite crystal structure.
Okay.
So if you look at this Alma Queen here, it has a distinct shape and overall, shape's probably the structure is the best way to look at it.
Right.
So to determine some minerals, you will look at their crystal structure. Now there are 7 distinct crystal systems that minerals fall under. There's like monoclinic, triclinic, cubic, tetrahedrons, all those different shapes were formed by their chemical structure. So a common one that most people have heard of is pyrite. It forms cubes naturally. So when people look at pyrite, they see these perfectly golden hued cubes. That's how it comes out of the ground, because of the iron that bonds with the minerals actually forms perfect cubes at its atomic level.
Cool.
So it's like Legos. If you build a block of Legos and then keep stacking more blocks of Legos on top of this square, it'll continue that shape unless
Right.
you alter the overall structure.
It's almost like a snowball.
Yeah.
Starts a small sphere
And then it just
ends a
builds
small
on top of
sphere
it.
because that is the natural way that it's all going to come together. Now, snowballs are different than the lattice work of molecules and things like that.
It's not
That is
too
so-
far off, but it
that's
does.
so fascinating that you can see the structure of the Alma Queen or any mineral on display here and know that at the atomic level, it starts more or less in that shape and just layer by layer goes out and it holds that shape.
So technically, if you were to break this, although we don't recommend doing that,
Please don't try. Yeah.
it would actually break into smaller versions of itself. It would follow that same crystal structure. Now that's called cleavage.
Yeah.
So cleavage is whenever you break a mineral and it will follow those planes of the structure and form little tiny versions of itself.
Yeah.
And so much like a giant snowball, when you're building a snowman, if you were to put a stick in it, it would change the shape somewhat, maybe a little bit. But that's what happens when you are forming a mineral and then you have something that is included or inclusion inside. So for example, behind you actually is a quartz that is included with rutile,
Wow.
which in of itself is a separate mineral, but
Yeah.
as it was growing, the rutile inside was forming and solidifying, and then the quartz grew around it. So much like the stick in a snowball, stuff can get mixed in during the process. Now, it didn't change the overall crystal structure of the quartz because there was more material of the silicon dioxide, which forms the quartz, to layer on top. But a lot of times, natural processes will interrupt or change varying structures. And so with the Alma Queen, the reason why it's so held esteem is because it doesn't have those inclusions or impurities. It is in its pure form, naturally formed beautifully as it is.
And there's this kind of, maybe it's a buzzword or something on Instagram or social media where it says like no filter needed.
Yeah.
I have adjusted the saturation of this video just to make our skin tones be natural. So this Alma Queen, I promise you, looks even better in real life, even more saturated. It looks like there's a filter on it IRL, which is not really obviously what's happening. This glass helps just be able to see through without any diffraction, without altering how it's, the light rays bounce back to our eyes. So in real life, it looks like you turned the saturation knob all the way up.
Perfect maraschino cherry.
Exact. Oh man, it almost does look like candy, like rock candy. It looks like you could lick this and what would it taste like? It wouldn't be sweet.
It would not be good. No.
It probably just tastes
and
like.
And as from a geologist standpoint, please don't lick minerals because some are actually toxic because of elements that are inside that can cause harm to humans. So some contain levels of arsenic or mercury. And even, funny enough, we can get copper poisoning from some minerals.
Wow.
And there's some that have, so there is a silicosis, which is caused by too much silicon. So if you were to crush up or break some minerals like quartz without proper, headwear, you can actually ingest too much silicon and it's not good. No. So always be aware of what you're handling and wash your hands after some because some minerals like cinnabar and realgar are also very dangerous.
On the moon, when astronauts are walking around on the moon, I've heard that the moon dust is actually extremely abrasive, very fine, very abrasive, and it was actually something that needed to be contended with in future missions, and they did the best they could. We had samples. I don't think we had. Do we have samples before Apollo? I don't think we had samples before Apollo.
I think Apollo missions were the first where they collected samples.
Right, because you have to kind of learn as you go. We'd never been to the moon before, and
just from the outside, it doesn't look like a problem.
Right, but can you speak to that? The fineness of that.
Yes, think of it, it's like
matrix.
Fine glass. It's very, very powdery. It might feel soft, but it can actually be glass-like texture.
Right.
So one thing that is interesting that we've now kind of delved more into in the last, I don't know how many years, but the geology of space, astrogeology. So there are specific people that are studying like geology of space matter, in particular the moon and samples we've collected of meteorites and things like that. So the Earth is made of space stuff. Right. As they say, humans are made of space dust. Mm-hmm. So everything that we have on our planet is from space. So we match what is found out there, but in just different forms.
Right.
And so, like, for example, gold. You'll see the new gold that we just recently got from Australia. Mm-hmm. All the gold we have on our planet is all the gold we've ever had. Right. And it was during the great bombardment of the planet. And it helped form our core, and it got molten, and then it changed, and natural processes moved it around. And as it formed, it cooled and brought up to the surface and then melted and moved around. And that's how we find gold naturally now, is in like flakes or nuggets. But it's all we've ever had on the planet. And so very much stuff we find naturally here can be found in its elemental form off planet. And so studying moon dust, we see the same type of material here on Earth, but just different. And so with that, it doesn't have the natural processes that change it, like wind, water, snow, sun, things like that. So it's a lot more abrasive. It's not eroded, it's not weathered.
Right.
So it's sharper and abrasive, and that's why it's very much different.
You think of rocks and pebbles in the river.
Even
Nice
sand.
and cement, it's all smooth. You look at sand under a microscope from a river or a beach, it's very smooth. Moon has none of that.
Nope.
So it's just microscopic
Sharp and
knives.
abrasive
It's really sharp. A question that we always, it's not really rabbit trails, but when a meteorite lands on Earth and they can say, where did this originate? And they can say, this originated from Mars. Or when we go to the moon and bring back samples of rock from the moon, we can say, oh, this originated from Earth. Moon rock is the same as Earth rock. How do you know that? You look at the isotopes.
Yep.
You can see the isotopes of Earth rock and isotopes of moon rock and see that they are very similar, if not identical. And you can also measure using radiometric methods, dating to see, oh, this moon rock, around 4.5 billion. Oh, this Earth rock, around 4.5 billion. Oh, this Mars rock, similar, but it aligns with its formation in the solar system. And the isotopes of a Mars rock do not match the isotopes of an Earth rock. An isotope of a meteorite that originated from Mars, which we have some in the museum, those isotopes line up with what we sample from Mars. So it's really cool on that kind of, at that level where you can kind of determine, where did this rock from space come from?
Yeah.
Some of the meteorites came from way out in the asteroid belt, maybe some from the Oort cloud.
And we've done things like that, but on a lot shorter terms, because we can at least determine briefly how old the Earth is.
Right.
And so like mountains, when they form, they have geologic signatures, like certain things that happen in a certain timeline, because the Earth is like a cake. It's formed layers.
Right.
So stuff that happened the longest time ago is always going to be at the base. So you can use that dating to determine, oh, it formed this time during this age. And then so we can do this sort of backtracking, and it's a lot more in depth than that. But structural geology will tell us how it formed, when it formed, and all sorts of stuff like that. So it's a lot more complex, but that's how you can kind of determine the age of the rock that the mineral formed in.
Right.
And they even can, from what I've noticed, I don't know exactly how it works, it's very complex, but they can determine the growth rate of minerals. So you can determine like how much material was available,
Right.
and then how long it took. And so some, like the one that briefly comes to mind is red beryl. It is very rare, and it doesn't grow very big because it takes a lot of chromium too. And because of that, you can actually determine the growth rate, and it's like millimeters per month, and it takes like 7 months to grow this big.
Right.
So, and of course, sometimes you have minerals forming on top of other minerals, and so you have to kind of do a little bit of inference saying, oh, this one was here first, and then this grew on top of it. So much like the rutile in quartz. So it's like fly in an ice cube, which formed first? So of course the fly was there before the ice had solidified, so the fly was there before the ice cube. So very much like that.
It makes me think, we'll start wrapping up here in a couple minutes. We could go on for hours. We could go on for hours about that. Then we'll do more, we'll definitely do more geology podcasts.
And it's always fun to hear people's questions, because I know it gets very complex, but.
Right. So something I'm reminded of is, I'm a layperson. I just kind of get to hang out with really smart people all the time. You might look at mineralogy, geology, and think, I know just enough not to realize you don't know anything. If that kind of makes sense. Oh, that's a red rock. That's,
and even I just scratched the surface. So.
Sure, and you can go to college for years. Doctors at the end, it's not that you know so much more. It's that now you know how to study better. Now you know what to look for, whatever.
Yeah.
But it's kind of like, I kind of relate it to car people. Car people versus non-car people. When you tell a non-car person what's a pickup truck, it's F-150 is the same as a Chevy. They're all the same thing. But a car person knows.
If you look under the hood,
the car person knows the displacement, who made it and where, how it came together, how they sourced the headers, how they know all the details. So a lay person like myself might just come look at the rock and say, oh, that's pretty. That's whatever. And then just, that's it. I know everything about Alma Queen because I looked at it with my eyes. No, there is an entire iceberg, which I just learned now is a mineral if it formed naturally. So there's a little peak of the iceberg of what we think we know about geology.
And then there's the bottom.
And then there's, everything underneath, oh my goodness. So it makes me kind of approach these different subjects of science with a little bit of humility, knowing that just when I think I know everything about it, it's not just rocks. It's a whole,
which is a whole nother topic in our own, because rocks aren't minerals.
Right, yeah, okay. That'll be for another episode. Real quick, with a few minutes we have left, I know it's a completely subjective question, but somebody brought up in that podcast in the comments a year or so ago, maybe more. Why would somebody, you approached this a little bit earlier in the podcast, but why would a geologist, a mineralogist consider, an enthusiast, hobbyist, anybody, consider the Alma Queen to be the best specimen of any mineral in the world, in their opinion?
Quick classification,
sure.
Size, color, and of course, just the desire for that mineral. Right. So a lot of times just liking something can stir people to want it more.
Right.
And much like anything, it's like if everybody has one, like that Starbucks cup, the recent Bear Star Cup, everybody wanted it. So the desire to have it was stronger. So the same thing, because it's the quality, the color, the rarity, it brings that desire. Right. And so more and more people would want that. But to be just plain and simple, this is probably the only specimen like it from that location anywhere in the world. Right. So the pure rarity of this piece is what makes it so, desirable.
If you want to see the Alma Queen, Houston, Texas, and this spot, this geolocation right now, mark it on our GPS. This is the only place in the world that you can see the Alma Queen. Mm-hmm. As I understand it, there is technically a bigger specimen of rhodochrosite elsewhere. I'm not sure exactly where it's kept.
I'm sure there are bigger pieces, yes, but
many still consider this in its presentation, how it comes out of the substrate or the matrix that it formed out of, the different facets and angles, the richness of the color. They all add up to. Yeah, I can totally understand why many hobbyists would consider, and enthusiasts and scientists would consider this to be one of the best specimens, if not the best specimens in the entire world found thus far. And that's crazy to think about. So this is a giant piece of rhodochrosite right here.
Yeah. And one other thing to think about is this particular piece is the only one like it in the world. No two minerals are the same. They don't grow identical. I mean, yes, they look similar, but they're not. It's not like hyper-realistic clones. They're not exactly the same. Each one is different. So you won't find one exactly like this. It's one of a kind.
Right. So
all minerals are like that. They're of themselves are the only ones. So you can come and see stuff that is the only ones like it anywhere in the world. Right. So everybody has that whole view that, this looks like the next one, but this is the only one, the only Alma Queen.
Right. Wyrex in our Paleo Hall, that's the only Wyrex in the world. That's the only T-Rex in the world with the best preserved feet in the world. That's
the tail missing.
And the tail missing, and the tail telling a story, the trace fossil. Things are very unique. This is one of the most, if not the most unique piece of rhodochrosite on planet Earth that we ever found this far, until somebody finds the one that's the size of an old Volkswagen Beetle. But as of yet, we don't know that to exist. So if you want a really good example of one of the best, if not the best, specimens of rhodochrosite in the world, it's this one that we're standing right in front of. And you can't see it on camera, but there's a guard. There's a guard that's always here keeping these things safe. So, Alex, thank you so much for coming on the podcast. We will definitely do it again.
Of course. Thank you so much.
You can always rate and share the HMNS Beyond the Bones podcast if you dig it, pun intended. A huge thanks to the wonderful Alex Ruff for his time and knowledge today. Be sure to follow the Houston Museum of Natural Science across all the popular social media platforms. And until next time, as always, I'm your mental curator, Johnny Hemberger, reminding you to stay safe, stay curious, and let you know that we can't wait to see you at the Houston Museum of Natural Science. Take care.